I'm Jiangfei Duan. This is Zhang. Today we are going to present the Parcae proactive Liveput-Optimized DNN training on preemptive instances. Nowadays, the LLM training is expensive. For example, the training cost for Llama 2 is expected to be approximately $4 million. The GPT-3 scale model costs about $5 million. So the cost is unaffordable for most organizations. One question to ask is, how can we reduce the training cost? Luckily, we found that cloud providers usually offer cheap spot instances, which can be utilized to reduce the training cost. On Azure and AWS, we can save up to 10 times or 9 times with the spot instances to do the DNN training. But as cheap as they are, spot instances are preemptible. This figure shows the trace of the total number of available P3 instances on AWS when trying to acquire the 32 instances. From the figure, we can see that the preemption is quite frequent. On average, preemption happens every 5 minutes, and in the worst case, it happens every minute. Therefore, the key challenge in leveraging spot instances is how to handle these preemptions efficiently. But before we discuss how to handle these preemptions, I want to first give some background on distributed DNN training. In single GPU training, we put the data and the model parameters on single GPU. When it comes to the multiple GPU training, we have several different parallelization strategies. The most commonly used strategy is the data parallelism. It replicates the model parameters on different GPUs and feeding in the different data for each replica. The second one is the pipeline parallelism. It splits the model parameters across different GPUs, and the different stages handle the same batch of data. And finally is the hybrid parallelism, which combines the data and the pipeline parallelism. In this presentation, we will focus on the last one, the hybrid parallelism strategies. So let's go back to the preemption handling strategies. There are usually two types of approaches. The first one is the checkpoint-based approach. For example, the Veruna published on USENIX 22. During the training, Veruna periodically writes checkpoints to a persistent storage and then continue the training. When it meets the preemptions, Veruna first do a reconfiguration to the optimal parallelization strategy with the remaining instances. Then it will load the latest checkpoints and continue the training progress. So this checkpoint-based approach has two disadvantages. The first one is it suffers from a huge I/O overhead, especially when the model is quite large. The second one is when preemption is frequent, the progress frequently rolls back and with a lot of GPU hours. So this checkpoint-based approach doesn't scale with the number of instances and model scales. And the second one is a redundancy-based approach. For example, the Bamboo on NSDI 23. Bamboo places two consecutive stages on each GPU. One is the normal stage and one is redundant stage. The redundant stage does the redundant computation for preemption recovery. So when it meets the preemptions, it will activate the redundant stage in place of the normal stage. Then it will continue the training progress without changing the parallelization strategy with the remaining instances. So the drawbacks of Bamboo comes from the redundant computation and memory overhead. It is quite hard for Bamboo to completely hide the redundant computation overhead. Besides, Bamboo also needs a longer pipeline depth to accommodate the redundant memory, the redundant stage. So Veruna and Bamboo are reactive and throughput optimized systems. In our paper, we want to present the proactive Liveput optimized system, Parcae. Parcae proactively plan for future preemptions to maximize preemption-aware throughput, which we call the Liveput. During the training, Parcae first does the availability prediction to predict the future preemptions regularly. It plans for future parallelization strategies to maximize Liveput. Then it continues the training and handles preemptions with our efficient live migration strategies. So Parcae achieved up to 10 times improvement on GPT-2 and GPT-3 training throughput compared with Veruna and Bamboo. Parcae Ideal used the preemption signal as our oracle to optimize Liveput. The performance of Parcae is quite close to the Parcae Ideal, which means our system is near optimal. So So let's dive into the details of our system. We first want to give the definition of Liveput for parallelization strategy D and P with the preemption V. Preemption scenario can be interpreted as where and how many failures happen on the parallelization strategy. For each preemption scenario, we will have a new parallelization strategy after the preemption. And the Liveput is the expected throughput of all these parallelization strategies. So intuitively, Liveput describes the expected throughput of a parallelization strategy by simultaneously considering its throughput and robustness under preemptions. So let's use that example to illustrate what is Liveput. Suppose we have 6 instances and they construct 2 pipelines and 3 stages. Each pipeline gives 15 samples per second for the throughput. If we have only one preemption, there may be 6 preemption scenarios since this is a preemption permutation problem. For all these preemption scenarios, we can maintain one pipeline with 100% probability to continue the training. Hence, the Liveput for this parallelization strategy with one preemption equals to 15 samples per second. So, given this example, we want to compare the throughput and the Liveput. Again, suppose we have 6 instances with 2 different parallelization strategies. The first one is 2 pipelines with 3 stages. The second one is 3 pipelines with 2 stages. So if there's no preemptions, the things is the same for the throughput and the Liveput. In the first case, we have 2 pipelines, and for throughput, we can have 100 samples per second. And for the second one, we have 3 pipelines. The throughput is 90 samples per second. And for the Liveput, since there is no preemption, it's the same as throughput. But things becomes different when there is preemptions. Suppose we have 1 preemption. In the first case, we can only maintain 1 pipeline after the preemption. So in the second case, we can maintain 2 pipelines after the 1 preemption. So Liveput for these 2 parallelization strategies becomes different compared with throughput. In the first case, we have already calculated the result is 15 samples per second. And in the second case, we have 2 pipelines. So the Liveput is equals to 16 samples per second. Okay, given all these calculations, let's consider maximize Liveput or throughput. If we want to maximize throughput, we ignore all the preemptions, and we always choose the first parallelization strategy as our optimal strategy. If we want to maximize Liveput, we should use different strategies considering the preemptions. If there's no preemption, we will use the first one. If there will be 1 preemption, we should use the second one to get the optimal parallelization strategy. So we build our system to, so this result shows maximizing throughput is suboptimal, and we build our system to maximize Liveput. Next, Zhang will introduce some details of our approach.
Thank you, Jiangfei. With theoretical foundations set, we're able to break down the spot instance training down to 3 sub-problems. First, how we're able to predict the Liveput. And second, how we're able to maximize the Liveput with selected parallelization strategies during this period. And third, and last questions, how we're able to gracefully handle reconfiguration and recovery between different preemption scenarios and cases. With that, our contributions unfold this way. So first, we present availability predictors to enable us to accurately predict the future instances in this part. And our second part is we present this Liveput optimizers for us to perform this strategy, Liveput optimized based strategy search over time. And last but not least, we also have this very gracefully handled live migration mechanisms to perform this migrations engineering methods. Liveput requires 2 ingredients, just as a reminder, strategy and preemption mappings. But here, our first problem encounter is that preemption mapping is very hard to get because it is not realistic to predict the preemption of individual instances. So we take this question under another lens. Fortunately, we're able to discover that the short-term instance availability is predictable. Let's take a look at the diagram here. So the horizontal axis is the number of times it persists, and the vertical axis refers to the number of available instances. So we're able to observe that the time series correlation of instance failure and recovery events on the scale of 12-hour traces. Statistical methods in this way are able to robustly give convincing predictions of future tendencies by looking at the past. Given this blue realistic trace, our prediction curve fits very truthfully with the past history. And this findings validates our assumption of time series predictions, which we're going to expand later. So when it comes to the observations, we predict that the future instance availabilities rely heavily on our past behaviors. And to refine these predictions, we chunk off these future time intervals down to the fixed size time intervals. And then we reduce this problem down to a time series forecasting problem of different available instances at hand. And then we build a predictor based on the instance availability in fixed time intervals in the future, and then we perform a series of statistical prediction methods to fix this issue. Now, with the prediction available, now we're trying to bridge the gap between the predicted instance availabilities and probability of preemption mappings. So assume that I get the intel that the two instances are going to fail in the next period of time. And the problem here is that how we're able to find the permutation of the failures given the positions of this machine is going to fail in the 3x4 hybrid parallel strategies. So our naive idea, of course, is to go with an iterative approach where we're just going to take the permutation and see the posterior probability of different mappings. But given the size of the modeling size, number of instances, and also this number of failures, this becomes increasingly unpractical. And therefore, we go through an approximate approach by sampling this approximate probabilities of different mappings with Monte Carlo samplings. And now let us go down into the Liveput-Optimizers design. So we start by predict the short-term availabilities in the next 3 intervals by looking at the blue interval past. And then we understand that for each instance availability at a time interval, it can support as much parallelization strategies available as it availed by this number of, bounded by this number of available instances. So our problem now becomes, given this availability intervals, how to maximize liveput with a strategy search. So in this way, we use a dynamic programming approach to exhaustively search the combinatorial optimization search space. And namely, to translate into English, I mean by we're able to obtain a sequence of parallelization strategies to adopt in the future to maximize training progress. And that's how the optimization search space goes into play. Okay. And with strategy set, our remaining challenge remains how to gracefully migrate between different strategies to handle preemptions. So compared with the traditional checkpoint restart methods where all instances are going to be killed and rebooted, we provide 3 lightweight solutions for each case. So in case 1, we have 2 failed instances, and they fail on different pipelines in different stages. We can just change the process group of the first 2 pipelines, and then salvage at least 1 pipeline out of these 2. And this is very lightweight because we only change about this like a P2P communication group here. That's how we call the intra-stage migration. In our second scenario, we propose the interstage migrations where failures occur on different pipelines but on the same stage. In this case, we only need to partially reconfigure 1 instance and then figure out a communication group. That's also very cheap. In the last scenarios, failures can happen on the same stage. In this way, we introduce the pipeline migrations, reconfiguring from current strategy to a more productive strategies availed by the remaining 10 instances. So to show some end-to-end experimental results, we select 4 curves representative of 4 different scenarios in this 12-hour trace histories. So let's break down into the terminology here. So the A and P refers to the availability and the preemption. And H refers to high, L means low. So same case goes for the D and S, means the dense and the sparse. So overall, our main message is that Parcae is able to achieve up to 10 times higher throughput in these 4 cases than the traditional checkpoint restart and the redundancy methods. But we also make sure that we also achieves better scalability towards number of instances in the cluster and the failures. So let's just look at the final cases where with the LASP, with a low availability sparse preemption cases. In this case, traditional methods just going to die away because they're always busy with reconfiguring from failures and not able to contribute real training progress. But in this way, Parcae is able to provide steady progress over time. And Parcae also achieves near optimal performances given the strategies play out by the Oracle strategies or relying on its own predictors to do the strategy search in migration. To summarize, Parcae proposes a proactive Liveput-Optimized DNN training methods on spot instances. Our methods achieves about 10 times higher throughput than checkpoint restart and then redundancy-based methods. We're happy to open source our code and happy to take questions. Thank you.